The chemical properties of carboxylic acids. Acid-base reactions occur because the OH on the COOH group acts as a proton donor, meaning this is a protic hydrogen, it can pop off and become H+. Acidic hydrogens are those that can pop off as H+. And our acid-base properties. They release H+ in solution like an acid. They have a sour taste like an acid. They turn litmus paper red like an acid. Their pH is less than 7 like an acid. And they react with bases and neutralization reactions just like an acid. The high molar mass carboxylic acids have a very dominant nonpolar R group, so are not soluble in water. But they still react with strong bases like sodium hydroxide and potassium hydroxides. Then the salts typically are soluble in water. So once you have a salt, you have a negative charge and a positive charge, and that makes it infinitely more soluble in water. And so just because the carboxylic acid wasn't soluble in water doesn't mean the salt won't be. A lot of times they are soluble in water once they become the salt. And that's pretty much what soap is. Long chain carboxylic acids with a plus and minus here. Because you have a very polar end which can react well with water, then you have a very fat-soluble end which can dissolve grease into little goblets. Substitution reactions. You can attack this carbon here. You first have to activate it, but then something attacks, kicks up these electrons, these come back, and you kick off your leaving group. OH minus will never leave, and so you can't just directly attack a carboxylic acid. First, you have to activate it some way so that it will react. And a good way to do that is with thionyl chloride. So thionyl chloride reacts with the carboxylic acid to form an acid chloride. And these are super reactive, so you can make all the other ones from this, because anything can attack here, kick these electrons up, and they come back down, and you can remove a chlorine very easily. So acid chlorides are extremely fragile molecules, and they break down very easily, and so you can use this to make every other carboxylic derivative pretty simply. So acid chlorides, again, extremely reactive, never found in nature. They're too reactive. If you breathe on them, they'll break down, so they're super delicate. And if they're exposed to water, like I said, they break right back to the carboxylic acid, so you have to keep them dry and safe to react them. If an alcohol attacks, you form an ester. If an amino group attacks, we form an amide. And here was the ester. Two carboxylic acids can react and remove water to form an anhydride. So one way to do that is with an acid chloride and then the salt of a carboxylic acid, or you can use a dehydrating agent like P2O5, and that will rip off this water molecule and give you an anhydride. Again, reacting an alcohol with a carboxylic acid gives you an ester. So formic acid and ethanol react. It's acid catalyzed, that's important, because here you gain an H+, and now you went from a bad leaving group, OH minus, to a good leaving group, water. So now your alcohol attacks this carbon, these electrons kick up, then come back down, kicking off water, and giving you your compound. So when you name the esters, we name the alkoxy group. This is the alcohol portion of the molecule, and then you name the carboxylic acid portion, changing the ic to the ate. So ethyl acetate, methyl ethanoate. So here we have methyl acetate, methyl from methanol, and acetate from the acetate. And again, acetate is so common, you almost never see ethanoate. It's almost always acetate. And methanoate, it's also pretty rare. It's typically formate, almost always. So here we see methyl propanoate. Here we would have propyl, 1, 2, 3, 4, butanoate. Here we would have Phenol, because it's just the phenol group there. Acetate, phenylacetate or phenylethanoate. Low molar mass esters. They're very volatile, nonpolar liquids at room temperature. And they're used extensively in paints, varnishes, and lacquers. Have a very characteristic and fragrant fruity odor. So here we see butyric acid has the unpleasant odor of rancid butter, but ethyl butyrate has the pleasant odor of pineapple. And so in general, esters are super good smelling. And so like octyl acetate will give you the smell of oranges. Hexyl acetate will give you the smell of apples. The pentyl acetates give you the smell of bananas. High molar mass esters. These are waxes. A wax is just a gigantic ester with gigantic R groups. Used in furniture and automobile wax preparations. They're very high molar mass esters and can include polyesters such as Dacron. So polyester is a polymer, as we talked about earlier in the polymer chapters. Just the polymer contains esters, which is why it's called polyester. Or polyethylene terephthalate, and that's PET, P-E-T-E, polyester, used in Mylar films, and it's what makes up Coke bottles, soft drink bottles. And they are given the recycling designation 1, and that actually corresponds to its density. Separating based on density is important so you don't jam up the equipment at the recycling plant, but that may have just been fixed by a new invention that can still deal with plastics of different densities. So that may be a problem of the past pretty soon. Cross-linked thermosetting polyesters. We have a preparation by reaction of trifunctional acids or alcohols as monomers, like glycerol. And so here's the reaction of glycerol and orthophthalic acid. The polymer formed is one of a group of polymers known as alkyd resins. And so we're going to draw the condensation polymer. And you attach to both sides, here and here. And we're making an ester. So pretty much you're keeping just this group right there. Hydrolysis, the principal reaction of esters. It can be acid catalyzed or base promoted. In an acid catalyzed reaction, this is like Fischer esterification. And our H plus will bind this oxygen. Water will attack. And H plus will bind here. And these electrons will collapse back, kicking off your OR group. Specific examples of acid-catalyzed ester hydrolysis. Methylpropanoate is broken back into propanoic acid and methanol. Methyl salicylate is broken back to salicylic acid and methanol. Base-promoted hydrolysis. Here we just use sodium hydroxide in a 1-to-1 ratio. And the OH minus is really strong. And it just comes in, attacks, electrons come up, come back down, and you kick off the OR group. So here we see ethyl stearate being broken down into sodium stearate and ethanol. Write equations for the acid hydrolysis and the base hydrolysis of ethyl butyrate. We have acid hydrolysis and base hydrolysis. You get the exact same products, only difference is with the base, you deprotonate the carboxylic acid into the salt form, because that uses an extra equivalent of sodium hydroxide. Glycerol esters, triglycerides, are how you find fats in animals. And you have a glycerol molecule attached to 3 fatty acids, forming your standard triacylglycerol, your triglyceride. Fats and oils are triglycerides. Fats come from animal sources and coconuts. Coconuts have saturated fatty acids, and therefore it's typically also a solid white fat at room temperature, whereas oils come from all the other plants, and you have a lot of unsaturated fatty acids. Common unsaturated fatty acids found in oils. We have oleic acid, linoleic acid, and linolenic acid, due to the degree of unsaturation. And here we see animal fats, cow butter, pork lard, beef tallow, and you don't see a lot of the linoleic or the oleic acids in here. Whereas with the vegetable oils, you see lots of unsaturated fatty acids and very little of the saturated fatty acids. And that is why animal fats are typically solid and vegetable oils are liquid at room temperature. Reactions of triacylglycerols. This is a reduction in which these reactions include hydrogenation and hydrogenolysis. So, using a catalyst and hydrogen gas, we can saturate some of those unsaturated bonds. And that's exactly how we make margarine. You take a vegetable oil like olive oil, and you run it over a catalyst with hydrogen gas, and so you start saturating a lot of those double bonds, and you end up with a soft semi-solid like margarine. And so margarine is hydrogenated vegetable oil. If you take it all the way and saturate the entire thing, you will have a solid fat shortening found in Crisco. When you hear cis and trans fat, that has to do with a double bond. And again, a trans bond, the major groups are opposite of each other. And the cis bond, they're on the same side of each other. Hydrogenolysis. Here, with enough catalyst pressure and hydrogen gas, you can actually break these bonds, giving you glycerol and your fatty acids. Acid hydrolysis. You can break this down into 3 fatty acids and glycerol using acid as a catalyst or enzymes. Alkaline hydrolysis. This is the making of soap, saponification. Sodium hydroxide saponifies and it attacks, kicking off these carboxylic acids to form the sodium salts, which are soaps, and leaving you glycerol. So write the structure of a triacylglycerol that has 1 unit each of stearic, palmitic, and lauric acids. And here we have 3 possible isomers. So stearic had the 18 carbons. Palmitic had 16 carbons, and lauric had the 12 carbons. And there's 3 isomers, because each one of them can be in the middle, and then the other 2 are at the end, so it doesn't really matter which side. The ends are ends here. So there's 3 different ways to write this molecule. 3 isomers, different molecules. Soaps are salts of long-chain fatty acids and are prepared by reacting fats or oils with sodium hydroxides. And again, sodium palmitate is a soap that is a sodium salt of palmitic acid. And soaps are useful because you have the ionic side, which rapidly reacts with water, and you have the fatty tails, which break up grease into small little globulates, which have the ion part around them. And so they turn them into small enough particles which are dissolvable by water, and then water can rinse them off. And so basically they break up the grease into these tiny micelles, which with their positive and negative charges are water soluble and can be removed with water. So soaps, the limiting cleansing actions of soaps and hard water occurs because the hard ions precipitate the soap out. And so if you have calcium, iron, magnesium in the water, it'll just bind to the fatty acid and precipitate it out as soap scum. And so soaps are ineffective with hard ions, which is why a lot of houses have water softeners to get rid of hard ions. Soaps are also ineffective in acidic solutions because they grab the proton and become the insoluble fatty acid, which does not dissolve in water. And now your soap is now contributing to the grease problem because it is soluble in the grease. Synthetic detergents. These are similar to soaps, except you typically have a sulfate or a phosphate head. So whereas soaps were all the salts of carboxylic acids, detergents are similar, but they have sulfate or phosphate heads instead of carboxylic acids. But it's the same idea. You have a fat-soluble part and a water-soluble part to break up grease. The advantage of detergents is that even hard ions will not make a detergent precipitate in hard water, and so you don't ever form soap scum from this. And here's a cationic detergent because it has a positive charge. A lot of them have negative charges, like the sulfate heads and the phosphate heads are negative, but some can be a quaternary ammonium salt and be cationic with a positive charge.